Now we are going to do another numerical for the flow rate determination. So the turbine which is shown in this figure, that it extracts 50 so turbine is installed here, and so what happens that the water comes from here and it impinges on this turbine. So it is kind of hydraulic turbine thing. So it impinges on the so these are all the things which happen in the dam, in hydraulic dams like Mangla Dam, Tabela Dam. So that is the basic function, that from the elevation the water comes, and then that potential energy is converted into kinetic energy for that fluid, and then that kinetic energy is converted into useful work inside the turbine which is installed at the end, right? So it extracts 50 horsepower, and 1 horsepower is equal to 550 foot-pound per second. So here it is joule per second basically, so that is the unit of power. So from the water, the diameter of the pipe is 1 feet, and the pipe is 300 feet long, and the friction factor for this pipe is given to be equal to 0.02. So minor losses are negligible. So determine the flow rate through the pipe and turbine. So in order to determine the flow rate, we know that volume flow rate is equal to cross-sectional area into velocity. So it means that if we can determine the velocity, then we can determine the volume flow rate. So because we cannot use the whiteboard due to some kind of technical problem with the data pen, so I am going to show the solution from the book. So let me go towards the solution. Just a minute. Let's see. Okay, this one. Okay, so this is the problem here, that the statement I have just read through this. So if we try to see that energy equation, that would be equal to, we know that, let me do it. So the energy equation, we know that is P1 upon gamma plus V1 scale upon 2G plus Z1 is equal to P2 upon gamma plus V2 scale upon 2G plus Z2. So let me just, okay. So HL plus HT. HL means that the head loss due to minor and major losses, and HT is the head which has been converted into useful work. So that's why it is coming on the right hand side. So if I show you here, now if we see this closely, at location 1, the gauge pressure is equal to 0, so P1 would be equal to 0, and because this is a large reservoir, so V1 would also be equal to 0. Then if you see the location Z1, so Z1, it is written that it is 90 feet, and then if you look at the point 2, where we need to apply the energy equation, because it is going into atmosphere, so it means that the gauge pressure gain, that is equal to 0, then the elevation, that is Z2 is equal to 0, and we have got free jet here. So it means that V2 would be equal to V. And then there is minor losses negligible, major losses are there, and turbine work in terms of volume flow rate. If you remember that, if we go back in slides, we discussed that. Let me show that. It was somewhere. Just a minute. And we discussed back here. If you see here that shaft work or turbine work, which is on this slide, you can easily see that that is equal to HP or HS is equal to power of that turbine divided by gamma, which is the specific weight, into Q, which is the volumetric flow rate. So that is HT, or here it is denoted by HS. So that is the thing which is here in the equation as well, HT. And HL, that is due to major loss, which is equal to F into length divided by diameter into V scale upon 2G. And V scale is the velocity which is through the 5. So now if we put in the values in this equation, as I have just explained, that pressure at location 1, pressure at location 2, V1 and Z2 is equal to 0, and Z1 is equal to 90 feet, and V2 is equal to V. Why V2 is equal to V? Because it is a free jet which is going out in the atmosphere. So V2 would be the same velocity which is, it can be taken the same velocity which is inside the pipe. Okay. So now, if we calculate the put in the values, so first of all, HL, that is equal to F into L upon D, V square upon 2G. Now, since because we don't know the velocity value, so it means that we cannot calculate HL in numerical terms. We can only calculate in terms of velocity space, because velocity space is repeating here. So we are going to calculate in terms of velocity space, and then for the next part we have got. Here we have got the turbine power relation in terms of turbine head in terms of power, and volume flow rate, as I have shown you on the lecture slide, that is equal to power divided by gamma, which is a specific weight, into Q, which is volumetric flow rate. So volumetric flow rate would be equal to velocity into cross sectional area. Cross sectional area is pi by 4 d scale, and then gamma was given to, it is equal to 62.4 in British pound system. So pound per feet cube, 62.4. Power it is given in horsepower, so we need to convert it into foot pound per second. So if you see that HT, it also comes in terms of velocity, because there is velocity involved in the denominator. So now if we put in the values here, all the terms on Z1 is 90 feet, and P1 is equal to 0, V1 is equal to 0, then V2 is equal to V square, Z2 is equal to 0, P2 is equal to 0, and then these two values, they are being calculated here. So if we put these values, so 90 would, that is the Z1 value, then this V scale upon 2 into 32.2, that is the dynamic head, which is here, V scale upon 2D, and then the next one is the head loss due to friction, 0.0932 V scale, and then the last term on the right hand side, that is 561 upon V, which is due to the turbine head. So now if we kind of rearrange this equation, this is a cubic equation. So we can use our scientific calculators to calculate the value of V, and we know that because this is a cubic equation, it would have 3 roots. If it would have been quadratic equation, then it would have been 2 roots for this equation, but because it is a cubic equation, we will get 3 values of velocity. So now if we get those velocities, one value is 6.58 feet per second, and the other value is 24.9 feet per second. So these two values are realistic values, and then the third value is minus 31.4. So that is a non-physical value. Why it is non-physical value? Because we all know that the velocity here would be going in this direction, in the positive x direction. So it cannot go in the reverse direction inside the pipe here, right? So it should be going from the higher location to the lower location. So the third value, which has been minus, so we can discard it. But these two values are realistic or feasible values, which would give us 50 horsepower. So now the question arises that how we can get two solutions for the given power. So that is very easy to understand, because if the velocity is 6.58 feet per second, what will happen? That we would have the volume flow rate would be low, because Q value is area into velocity, but then the HT value would be higher. Why is that? Because velocity is appearing on the denominator in the this turbine work, but it is appearing as the multiplication. Q is equal to AB, if you remember. So in the first case scenario, when the velocity is low, then the volumetric flow rate is low, but the head which is being used in turbine, that is 85.3, but power is the same. Why that? Because velocity is also being here, so even 85.3 is here, but because the velocity is here, so it would give us 50 horsepower. Similarly, if the velocity value is more, sorry, let me Just a minute. Okay. No. If the velocity value is more, then I think we have lost that. Oh, okay, yes. So we were here. So I have discussed the case when the velocity value is 6.58 feet per second. Now, if the velocity is more, 24.9, then HL value would be more. HL value, which is the head loss in the due to friction, and consequently HT value would be less, right? But because the velocity is more, so the power would be same, 50 horsepower. So it depends on our pump specification whether we want to have more volumetric flow rate to get 50 horsepower, or we can get less volumetric flow rate. It depends upon our choice that whether we select a pipe with a higher volumetric flow rate or the less volumetric flow rate. It would give us the same horsepower which we want to extract from the that turbine, hydraulic turbine, right? So if there is any question you can ask, because it is a very practical problem which we usually see in hydraulic dams. So that is the same phenomena which is used in hydraulic dams. So if there is any question you can ask, otherwise we can discuss the third type of problems, which are when all the flow variables are given except the pipe diameter. So we need to determine the pipe diameter. So that is a quite complex process, and I will try to explain it from the slides as well. So I understand that today's class is not the ideal one because we cannot use the whiteboard, but luckily we have got the solution in the book. So I have explained. If you have got any problem in understanding, you can always ask me. Otherwise, we move on to the next problem. Okay, so it seems that everyone is satisfied with the explanation of the numerical problem. So now we move on to the third type of problem, which is where we need to determine the diameter of the piping system and all other flow conditions like fluid properties, then flow properties, and then the pressure drop, they are given to us. So now we are going to discuss this type of problem. So we have done this problem up till now. So now this is the third type of problem, and by chance I have done the solution as well on the lecture slide, so it would be we would be more comfortable to understand this from the lecture slide here. So here properties are given: the viscosity and density value flows through a horizontal galvanized iron pipe for which the surface is given, which is epsilon 0.0005 feet, and it is flowing at a rate of 2 feet cube per second. So volumetric flow rate is also given. The pressure drop is to be no more than 0.5 psi per 100 feet of pipe. Determine the minimum pipe diameter which would achieve this constraint of the pressure drop, which shouldn't exceed 0.5 psi per 100 feet length, right? So first of all, we write down the data which is given in this, which is known to us from the problem statement. So known data is fluid properties, yes, rho and mu. Then surface roughness value, because we need to use epsilon upon d to calculate the friction factor from the Moody chart or Holbrook relation. And then volumetric flow rate, that is also given. And then pressure drop per 100 feet of pipe length, which is beta P upon L, that is also given. And we need to, and the assumptions are horizontal pipe, which means that there is no elevation difference, that one is equal to that two. And then the second assumption is because there is no mention of change in pipe diameter, so we can say that the pipe is of uniform cross section. So it means that the velocity at section 1 would be equal to velocity at section 2, because the volumetric flow rate Q is equal to AB. If it is same at the two sections and the cross sectional area is same, then the velocity should also be same to conserve that volumetric flow rate. Now we need to calculate diameter of pipe. Now the problem with the calculation of diameter of pipe, that it appears in essentially every term. For example, that if we want to calculate volumetric flow rate, then okay, first of all we write that burning energy equation between two pipe locations having 100 feet of length. So one is the entrance of that section and two is the exit of that section, which is 100 feet apart. So the energy equation would be something like this, and HL is the here we have got major and minor losses. Now one thing which we need to also assume that there are no minor losses. Why that? Because there is no mention of any minor losses as well. So that's why we are discarding minor loss in this relation. So HL is uh, only only due to the major loss due to viscous effects in the pipe. So now if we want to calculate, if we put the values, so P1 and P2, they are P1 minus P2, that is given to us 0.50 psi, and then Z1 is equal to Z2, so they would be cancelled out. V1 is equal to V2, so that would be equal to V, and so the second term on the left hand side and the right hand side, that would be equal to 0. It means that they would be cancelled out because they are equal, and then here we are left with P1 is equal to P2 plus Fl upon D rho V square upon 2. Right. Now if we see that in this equation, which is P1 is equal to P2 plus Fl upon D rho V square upon 2, we have got how many unknowns? One is the friction factor and one is the diameter of the pipe, right? And then what is the third unknown? That is the velocity, because we do know the volumetric flow rate, but we cannot calculate the velocity directly. Why is that? Because cross-sectional area also involves the diameter of the pipe, which we don't know, right? So velocity is also a function of diameter. Then this friction factor, that is also a function of diameter, because epsilon upon d is required to calculate the friction factor. And then the second parameter which we need to calculate friction factor, that is the Reynolds number. Because if you remember the Moody chart, that is function of Reynolds number and as well as epsilon upon d value. So we can easily see that the problem becomes quite complex because we don't know, we have got many more unknowns. So it means that first of all we will try to see that what are the equations for that. So from this equation, this above equation P1 minus P2 is equal to Fl upon D rho V square upon 2, we can write it in terms of write this, that P1 upon P1 minus P2, that is given to us in the data that it should be not less than 0.5 psi. So if we want to convert it into pound force per feet square, so we will multiply it with 144, right? Because we are converting per inch square into per feet square, and then that is equal to Fn upon D, and length is 100 feet, and then rho V square upon it is rho V square upon 2. So rho value is 0.00238, and then 142 is written like that, and V square we have written 2.55 upon D square here. So diameter becomes a kind of 0.404 friction factor base to power zero point 0.2 or 1 by 5, right? But it doesn't solve anything because diameter is also unknown and friction factor is also unknown. So what to do now? Because we don't know not the diameter and friction factor. So what we try to do that we try to get as many unknowns, as many equations as there are unknowns. So then we try to calculate or write the Reynolds number in terms of diameter. We know that that is equal to rho Vd upon mu. Then diameter is again unknown to us, and then velocity is also unknown. But because it is written in terms of diameter, so we have put it here 2.55 upon d square into diameter. So d would be cancelled with this d square. So Reynolds number can also be written in terms of diameter, and then relative surface roughness, that is epsilon upon d, that is again 0.005, that is given in the data, and the diameter is here. Now we can see that we have got how many unknowns here. We have got four unknowns. One is friction factor, one is diameter, then and this relative roughness, which is epsilon upon d, and then we have got Reynolds number. And then we have got four equations or chart. What are the four equations? One is this equation epsilon upon d. The second equation is Reynolds number. One, and the third one is diameter as a function of 0.404 into friction factor. What is the fourth equation? Fourth equation can be Moody chart. So there we would try to find friction factor, or we can use Colebrook relations, which are also based on that Moody chart, right? So it means that we have got four equations and four unknowns. So it means that it would require some kind of iterative solution for this. So it means that iterative solution means that we would assume a parameter and then we would do the calculation, and in the end we will match the assumed value with the calculated value. So if that value is equal, then we will say that the solution is good enough. Otherwise, we will repeat the iteration with the new calculated value of the parameter. So in this case, we for the pipe flow situation, we usually use friction factor, and then we would proceed with the calculation, and in the end, we again calculate the friction factor. So how it can be done? So let's see that. So first of all, what we do that we assume that friction factor is 0.02. So it is just kind of an educated guess. So if I take you the Moody towards the Moody chart, so this is here. If you see that 0.02 is this value where the mouse cursor is. So we are just taking an educated guess that the friction factor is in the middle of this chart. So it is kind of in the middle of the chart. So we have assumed that friction factor would be equal to 0.02. So once we get this value, then we can proceed with the calculation. So assume S is equal to 0.02, and then once we get friction factor 0.02, then we can calculate diameter. How can we calculate that? Because we know that diameter is equal to 0.0404 into friction factor raised to power 1 upon 5. From there we calculate diameter. Once we calculate the diameter, we can calculate the Reynolds number, right? Because Reynolds number in that diameter is unknown. So diameter is unknown, and then we can also calculate epsilon upon d. In that we have got. So once we get Reynolds number and epsilon upon d value, what we do that we take these two values and go into the Moody chart, 8.5 into 10 to the power 4 and 0.0028. So we go into the Moody chart, so 0.0028, if we try to look at in the Moody chart. So epsilon upon d 0.0028. So it means that it would be somewhere here, and Reynolds number is 8.5 into 10 to the power 4. So it is kind of somewhere here, right? You can see that it would be more than 0.025, and in between 0.03. Right? If I repeat, 0.0028 would be somewhere here where the mouse cursor is, and 8.5 into 10 to the power 4 would be somewhere here. Right? So it would be around in between 0.03 or 0.025, or you can equally use this formula, right? This code group relation to calculate the value of friction factor. So if we calculate the value, so that would be in between 0.025 and 0.03. So we can see that from the Moody chart. So once we get that value, if that value is equal to 0.02, then we can stop the iteration. But if it is not equal to the value which we have assumed, then we need to replace the assumed value of x in step 1 with the one which is determined from the Moody chart, and repeat the procedure until the solution converges. So if we see, as I explained from the Moody chart, that value was in between 0.025 and 0.03. So they have said that this value is 0.027. So from here we are going to do again the calculation diameter, then epsilon upon d, and then Reynolds number. So now from the Moody chart, if we against these two values, Reynolds number 80,000 and epsilon upon d 0.026. From here, if we see that it becomes 0.027. Now you can see that they are, I think, this value 0.027 and 0.027, they are exactly matching. So it means that after the so it is usually it converges in 2 to 3 iterations. But if the initial guess is very different from the actual value, which might be the case, then maybe it would require more iteration. But usually it takes 2 to 3 iterations to get the acceptable convergence of the solution. So it means that we require some kind of iteration if we are to be given pipe diameter determination. Now the question is that if in the exam situation, if I give you the question of determination of diameter, then maybe it is quite possible that I can give you the first assumption that what you need to assume the value of fixing factor, and then I can suggest that how many iterations you need to perform to show that you know this procedure. Maybe I would say that 2 iterations are enough, or maybe if I think that 3 iterations are required, so maybe I can ask for 3 iterations, but not more than that, right? So we can easily see that these 3 types of problems which we discussed for the calculation of major and minor losses and pipe discussed piping system design, we have got 3 types of problems, and the third type in which we need to decide about the diameter of the piping system, that is quite challenging. The first 2 types are quite straightforward, right? So if uh, these 2 types of problems are given to us, we can get the calculation done in one step or in one go. But if it requires the calculation of diameter, then maybe we require more than one iteration to get the convergence of the solution. So that was all about uh, chapter number 8, which is viscous internal flow. Now, if I because the book is also open here, so let me see that. Okay, maybe not. Just a minute. Okay, so we have. Discuss the viscous pipe flow, which is chapter number 8, and now we are going to discuss chapter number 9, which is flow over immersed bodies. So it means that it was chapter number 8 was regarding internal flows, and now we are going to discuss the flow which is external flows, right? So before we start discussing that, because I have given you quite a lot of homework practice problems, so I'm sure that you would do these problems in your own time, but just to make sure that you at least do certain numerical problems, so I would also give you a second assignment in which there would be uh, 4 or 5 problems which would require a kind of solution for these 3 types of problems, right? So, and every one of you would have to do it your own calculations, because in each calculation, in each numerical, there would be different numerical values depending upon your registration number, right? So I would give you maybe 1 week for that. So I would maybe in a couple of days I would upload that assignment on MS Teams, and I'm pretty much sure that you are working towards the term project which I have given you already, and the deadline is 31st May, right? And please, because that is something which you need to be very serious, because that is a skill you should have before you go into industry, that you can use some software as well. So if you are facing any problem, so please let me know, and then we can discuss it in one-to-one meeting. Whatever problem you are facing for the software, anything you are not understanding in doing the simulation, I can always be very happy to help. Right? But you need to kind of develop the skill to learn by yourself, or any software is given the opportunity. Right? So I would kind of reiterate this, that these numerical problems which we do here, that is very, what you can say, that is very rough design. Usually, the assumptions we take for these numerical problems, they are not valid in most of the engineering applications. So, in industry or inside that actual job situations, you have to use software or experimental setup to get certain values for the design of any engineering application. So, please try to take software skills and then experimental labs, take it very seriously, because at the moment, it looks like that your CGPA only depends on these numericals, but in actual situation, it depends that how much you are good at the general understanding of the subject, and how good you are at using those software, how proficient you can use those software. So that would determine that how good an engineer you are. So that is something I am telling you from my own experience, and maybe many would tell you, many seniors would also tell you. So please take it seriously to run software or all the labs we do for the experimental purpose. Take it very seriously. So now we move on to maybe we can take 5 minutes break. See that we have just discussed the relevant topics from chapter number 8, which was viscous flows in pipe, right? And now we are going to, so basically we discussed the internal flows. So now we are going to discuss the external flows. So it means flow over immersed body. So immersed body means that the body is immersed in the fluid and fluid is passing over that body. So can anyone give me an example of such flows where we have got external, these things come into external flow? So, as I have mentioned that the application as Hassan, as I think your name is Hassan Mustafa, I think, so he has rightly pointed out that flow over aeroplane, missiles, vehicles, ships, submarines, fish, flow past buildings, planets. So all these comes under the category of external flows, or we also call it flow over immersed body, right? So now in these situations, the object is completely surrounded by the fluid, and the flows, as I have pointed out earlier, that these flows are termed as external flows. So chapter number 8 was all about internal flows, and chapter number 9 it is about external flows. So in internal flow, that is bounded flows, and external flow, that is we have got fluid solid interaction at the surface of the solid, and then on the other side there is no limit, there is no boundary, right? So the boundary layer can grow uh, as much as possible because there is no limit on the other side of the flow. On one side we have got flow interaction, like if I show here, it is the flow over cause, and then you can see that the fluid which is in contact with the this car surface, that would have zero velocity. But if we go far away from the this car surface, then because there is open atmosphere, so it means that there is no limit, and then boundary layer can flow infinite. If this length of the car is infinite, then the boundary layer thickness would also be infinite. But as we know that all the practical objects, they are of finite length, so boundary layer thickness is also finite. And what is the motivation to study the external flows? That in this we want to calculate that how much drag force is being applied by the fluid on the object, right? Because that object, like if it is a vehicle or aeroplane, that has to overcome that drag force to move forward. So if the drag is less, then the fuel consumption would be low. And if the drag is more, then the fuel consumption, that is the power required to generate that power to oppose that drag force, that would be high. And for the ground vehicle, drag force is the major thing, which is the design criteria, because we want to limit the fuel consumption. Like in cars, basically they are quite thin. Like the frontal area is very low. It means that the flow is very that bodies are streamlined bodies. So it means that we have got less drag force on that. But if it is a bus, then the frontal area is more, and like a truck or a bus, then for those cases the consumption of fuel is quite high as compared to some cars, right? Like Formula car racing, they are very thin, kind of streamlined. It means objects like the frontal area, or the area on which the flow is going to strike that surface, that is very low. So that drag force is very low. And the second parameter, which is of critical importance when we talk about airborne objects like missiles, aeroplanes, fighter jets, that is the lift force. So drag force, it is in the direction of the flow, parallel to the flow, and the lift force is usually the force which is perpendicular to the flow. So basically, we need to have that lift force in order, so that the aeroplane can fly, and then those rockets and spaceships can travel in air. right? If there is no lift force, it would be quite difficult for those airborne objects to travel, right? So, because all these external objects, the flow around external objects is quite complex. So, usually we rely on the experimental investigation of these flows. Like we usually prefer to have the empirical correlations from the experiments which are to be conducted in the lab environment. Like in chapter number 7, we discussed those dimensional analysis like Buckingham-Pi theorem, that how to make the critical variables dimensionless, and then to reduce the number of variables, and then conduct the experiments by making a prototype by making a small model for its testing in the wind tunnel or water tunnel. That was basically modeling, and then how to correlate the results which are obtained from that scaled down model to the actual system. So that was similitude, right? So usually for the external flows we use those kind of studies or experimental investigation, right? So you can easily see that all the knowledge which we learned before, that is going to be used in the subsequent chapters. So please take all the chapters seriously, because they are all interconnected. So if you miss, or if you are not very good in the previous chapters, it would be difficult to understand these concepts, because these concepts would come from the previous knowledge. So please try to make a point that you understand the basic concepts. Okay, so now a body which is immersed and it is in a moving fluid experiences a related force due to the interaction between the body and the fluid surrounding. Right. So whenever the fluid is going to strike the body, it would apply some force on the body, and then as a reaction, body would apply the same force on the fluid. Right. So basically we can do the analysis in two ways. Usually vehicles are moving, and if it is moving in stationary air, then we can say that vehicle is moving and the air is stationary. But would we for the purpose of analysis in lab or in software, what we do that we keep that vehicle constant or object constant, and we make the flow around that object. So in that way, it is quite easy to do the analysis rather than the actual. Because if the a car is moving in a stationary air in from left to right at 50 meter per second, so we what we can do that we say that that car is stationary and the air is flowing from right to left with 50 meter per second. So it would eventually give us the same forces as it was the actual case, right? Only the frame of reference has been changed. So in NCL we usually keep the object stationary if it is like a vehicle, and then we make the flow past it. So in this way, the analysis is easier to be done. Otherwise, we have to regenerate the grid, and for if the vehicle is moving, then we need to generate mesh at each time step, and things become very complex. For the turbo machinery, we need to do that usually. So there are different types of flows. So two-dimensional flows, those are the flows in which, let's consider we have got a cylinder over which so the length of the cylinder is inside into the board. So what we see that it is kind of essentially a two-dimensional flow, because at each span, at each spanwise direction into the board, the flow would be the same. So we can say that we can assume that this flow is two-dimensional. And then another type of simplification for the bodies are the flow category. That is, if we have got axis symmetry body or axis symmetry flow. Like here, this is kind of a projectile which is moving in air. You can see that if you draw a line x-axis, so it is kind of symmetrical about its x-axis. So we don't need to do the analysis for the whole projectile. Instead, we can only do the analysis on this half section, right? And for the two-dimensional case as well, we only need to do the analysis for this circular cross section for the cylinder, and it would be applicable for the entire length which is into the board. So if you have used the fluent module of and since workbench, in the beginning it asks us to define that whether the flow is two-dimensional or three-dimensional. So if it is two-dimensional, it becomes quite easy, the simulation. If it is three-dimensional, it becomes very computationally challenging to do the simulation, right? And then in most of the cases, we have got three-dimensional flows. It means that we cannot apply any kind of simplification. Instead, we have to do the analysis on the entire body, and that is kind of three-dimensional flow, right? So it depends upon the application. So if we can reduce the computational cost by assuming that the flow is two-dimensional or axis symmetric, then it can greatly reduce the computational effort which is required to do the analysis. And the purpose of the analysis, please remember that we want to calculate the drag and lift force on the object, right? Because that would determine that how much fuel we are going to burn in order to move that object, right? If it is a moving object, or how much shear force is going to act on that surface if it is a stationary body. Okay, so as I have told you in the beginning as well, that there are two types of bodies in terms of the frontal area of the flow. If the frontal area is very small, frontal area means that where the flow strikes. So, like for this racing car, like which is shown in the figure, you can see that it is a very streamlined body, and this aerofoil as well. You can see that the flow is going to come from here. This is the leading edge, and this is the trailing edge, right? This is the leading edge is the where the flow, if it is coming from left to the right. So this is the aerofoil, which is usually the cross section of wing of the aeroplane. So that is the basically the aerofoil. We call it aerofoil, right? So this is also a streamlined body, because while that streamline, this is the frontal area, right? So the frontal area is very small as compared to the total surface area. Surface area is very large for this, but the frontal area is very small. And similarly is the case for this car, that the frontal area on which the air is going to strike, that is quite small because it is a streamlined body, right? And the surface area is quite large because it is quite long. On the other hand, we have got some bodies, we call it blunt bodies as well as block bodies. So like parachutes, which is going in the coming down. So we have got very high frontal area, and that is something which we use for our advantage. Because if the frontal area is more, the drag for the negative lift, it would generate, that would be more, right? So negative lift means that not positive lift, because in this case it would reduce the speed at which the paratrooper is coming down, right? And then here you can see as well that the frontal area is very large. So it means that they are quite tall objects with very small length. So length is small and their cross-sectional area is more. But here the length is more and the cross-sectional area on which the flow is going to strike, that is more. So, if we talk about any bus, like Divo bus, or there are many passenger bus, versus in that case, the frontal area is more, right? And that is, we can call it kind of blunt bodies. And one of the major characteristics of blunt bodies is that there is flow separation happens in the wake region. So wake region is the region downstream of that object. Like upstream is something where the flow is coming, and after passing through the body, it would go downstream. So for the blunt bodies, the major thing which happens in the downstream region, that there is a flow separation, and we call it wake region, where the velocity is different from the free stream velocity, right? So that is the case where we experience some high pressure region on the front hand side, because there would be a stagnation pressure on the front because the velocity is zero, and then because here there is a flow separation, there would be a vacuum. So in vacuum, the pressure would be very low. So there would be pressure drag. Pressure drag means that on the front pressure is high, on the back pressure is low. So it means that the pressure differential would result in a force which is pressure drag force. And the other drag component is the wall skin friction drag. Skin friction drag means that is due to the wall shear stress tau omega into the this surface area. So for the streamlined bodies, the skin friction drag is more. Skin friction means that due to the shear stress on the surface, and pressure drag is very less because the frontal area is very, because there is no flow, minimal flow separation in the wake region, right? But for the blunt bodies, the pressure drag is more. Why is that? Because the pressure difference between front and back is more due to the flow separation at the back end of the object, and the skin friction drag, that is very low because the length of the body is low, so the area upon which the flow is having the shear stress, that is low. So I hope that you understand this point, that there are two components of drag. Let me repeat. One is skin friction drag, and that is due to the wall shear stress on a streamline body, right? And then pressure drag, which is dominant in the blunt bodies when there is a flow separation at the back end. So pressure at the stagnation is maximum, and at the back end there is flow separation, wake region, there is essentially the negative pressure. So that's why we would have a kind of pressure differential at the frontal and back edge. Now that was something about the drag force. Now if you look here in this figure again, for the aerofoil, there is another thing, that is a perpendicular arrow. This arrow which is in the flow direction, that is the drag force which the fluid would apply on this body, right? And this perpendicular force, flow, mind it that flow is coming from left to right, and here that the perpendicular arrow, that is something which is the lift force. So the lift force, how can it be generated? If you think a little bit on this, it is very easy to see that if the pressure on the lower side is more as compared to the pressure on the upper side, there would be a net force in the positive y direction. So it means that here the flow should come from here. So if the flow is coming from downward side, so it would kind of push it on the upper side, and we would have a flow separation here on the upper side, and on the lower side the pressure would be more, on the upper side the pressure would be less. When there is a higher pressure on the lower side as compared to the upper side, we would have a net force in the positive y direction, which would produce the net lift for that object, right? And that lift is required for aeroplanes, missiles, rockets to travel in the air, right? Okay, so that was something which we talked here. So after that, now that was lift and drag, which I have just explained on this slide. And for the drag, I have just told that there are two components. One is skin friction drag, and the other one is pressure drag. So when anybody moves through a fluid, an interaction between the body and the fluid occurs. This effect can be given in terms of the forces at the fluid body interface. So these forces can be described in terms of the stresses. One is the wall shear stress, which gives rise to wall friction drag, and then normal stresses due to pressure, which gives rise to pressure drag as well as the lift force, right? As I have just explained, right? So the thing I was mentioning about the lift force here, lift force here, you can see that here the flow is coming from here and from the left to right, and then you can see one thing, that positive pressure, it is shown on the arrow going here from the bottom to the from the bottom. So it is trying to exert pressure from the bottom side, and you can see that that pressure profile becomes negative here on the upper side. Why is negative here? Because when the flow would become here, right here at the stagnation point, after that when it would travel on the upper side, so that would be here. There would be some kind of flow separation. Now that flow separation, you can easily see that whenever there is a bump in the road, like a speed breaker, if you are in a very jolly mood and you want to have some kind of elevation, so you can try to speed up your vehicle, and you can see that there would be some kind of jump your vehicle would see from that bump, right? But usually because we want to avoid that, so that's why we apply some brakes so that there wouldn't be any jump in the vehicle. So that is the reason, because we don't want that kind of jump in the vehicle. So that is the same thing with the fluid, that once it go towards here, so it would kind of jump from this surface, and there would be kind of a flow separation here. When there is a flow separation, there can be a possibility of negative pressure here. Negative gauge pressure we are talking about, right? Absolute pressure is not negative, but gauge pressure, that is negative, right? So it means that if that is negative pressure, that is also going upward, because we know that pressure usually is a compressive force. If it is a positive, so if it is a negative pressure, so it would also point towards upward direction. So the net force which is being on this would be upward, because all the forces is the upward direction. So that was the creation of lift. And then the second concept is for the drag force. Now that is on the explained on the bottom surface. You can here you can see the arrows going from left to right on the arrow for surface. So they are showing the force which the this fluid is exerting on the fluid on this in the flow direction. And so it tries to move this aerofoil in this direction, right? So that is kind of the force which the aeroplane being kind of get. Right. So that was the figure A was about the creation of lift force, and here it was about the creation of drag force. And for the aerofoil, the major drag would come from the wall friction drag, right? Not from the pressure drag, because the frontal area on the front side and back side, that difference is very low. And after this body is ended, there wouldn't be any flow separation, so there wouldn't be any pressure differential between, very minimal pressure differential between the stagnation point and the or the leading edge and the trailing edge. Leading edge is the place where the flow first strikes the object, and the trailing edge is the last point of contact. And if we join the leading edge to the trailing edge by a straight line, we call it chord line, right? And that straight line is also defined the chord length for aerofoil. Right. So I have told you about maybe I have tried to explain it in detail, that how drag and lift are generated due to the interaction of fluid with the body, right? So drag force is the component of force parallel to flow direction, and lift force is the component of force normal to the flow direction. The resultant of the shear stress and pressure distribution can be obtained by integrating the effect of these two quantities. So, if we say that we have an object which is inclined like this, that the angle here, if we try to, this is theta angle, then this angle would be 90 minus theta. If I try to show it, but if I extend this line and if it combines here, then it would be 90 minus theta, because it is theta, it is perpendicular angle, so it is 90 minus theta. So from there, if we try to find the net force on this differential area, this blue line, that is dA, it is the differential area of the surface. So if we want to calculate the x component of forces, which gives rise to drag force, that would be equal to P into dA into cos of theta, P dA cos theta. So that is right. And then tau omega sin theta, because for the tau omega it would be a cos of 90 minus theta. Because here if we extend this line, this axis would be this here the angle would be 90 minus theta, right? So that's why cos of 90 minus theta is sin theta. So similarly we can calculate dFy, which is going to give rise to lift force. So that would be minus PdA. Now why it is minus? Because it is in the negative y direction. Because pressure is always a compressive force. So that's why minus is there. dA, why we multiply pressure with dA? Because we want to convert pressure into force. So pressure is Newton per meter square Pascal. So if we multiply it with dA is this surface area which is shown here, right? And so, and again, shear stress is units of shear stress is Newton per meter square. So it would be we are going to multiply it with area. Now that we have calculated for this only this small area dA. Now, if we want to calculate the net force in the x direction, so we need to integrate all the forces on these differential areas from which this body has been comprised. Like here, dA was only the section here, the mouse where the mouse cursor is, and then the next dA would be this. Then all it would have many small differential element, cross-sectional areas. So if we want to calculate the net force in x direction, that would be by the integration over all these small differential areas, right? So it means that total lift and drag that can be calculated by the integration when we try to integrate these things over entire surface of this object, and then we can calculate drag force and lift force. Now this drag force and lift force, they depend upon the geometry of the geometry, that how much bigger is this aerofoil. So let's suppose if this is of an object which is this aerofoil, if it is being tested in a wind tunnel, it would be very small. Like all length would be 1 meter, maybe less than 1 meter. But if we talk about the actual airplane, this can be easily 100 meters, maybe 50 meters being called length. So the forces depend upon the size of geometry. So we learned from chapter number 7 that if we want to compare different things or characteristic of any fluid, so then we want to show them in some non-dimensional parameters, which we also call them pi terms. So this drag force and lift force, we define two non-dimensional parameters. One is called coefficient of drag, which is CD, and it is very common in fluid mechanics application. Even you can calculate this CD and CL values for any by using your MC simulation, which you must be conducting these days. So CD and CL, they can be calculated by the post processing in ANSYS software. So that is basically, if you want to define CL, that would be equal to lift force divided by half rho u square into area, right? And CD would be equal to drag force divided by half rho u square upon area. So it's because the denominator should be the unit should be force, like Newton, because the because here we have got lift force and drag force on the upper side. So now this area can depend upon the application. So if we have got a blunt body, then this area can be frontal area. So frontal area would be diameter into length, because if we see it from the front, if we would see a rectangle, we can easily see that if we see it from the front, this cylinder, we would the area on which the fluid would be striking, that would be kind of a rectangular shape, which is diameter into length, right? And if it is a streamlined body, then as I defined, as I have told you, that there is a chord length, that is the line which joins the leading edge with the trailing edge. So that is here, that is shown by this small l, this small c, chord, we call it chord length, chord, into length is the span wise length of this. So in this, it is the surface area, c into l, right? So it means that it depends upon the shape of the body, that is a blunt body or it is a streamlined body. So this area can change depending upon the application, right? So that is written in the last bullet point. So, like, just to give you an example, that there is a Toyota sign, which is a model. Now you can see that frontal area on which the flow is going to strike here, that would be very big area here, right? Because there would be this area and then this window, which is also kind of very straight frontal area. So here you can see that CD is equal to 1, area is 25, so this frontal area is 25 feet square. So CD into area, that is 20, it means that CD into area, that is 25 feet square, right? So the force would be consequently it would be very high, because that would be multiplied with rho into u square, right? Half rho u square. If we want to calculate drag here, so CD into area is 25, so it would be multiplied with half rho u square, right? But on the other side, if we have got a racing car, like it is shown on the right hand side, so here the CD value is very low, because it is a streamlined body. So the surface area which is here, that is very less as compared to this. So the drag is 2.8. So it means that it has got like 10 times 25 and 2.8. It is almost 10 times less drag force. So that's why it would travel much faster with a low fuel consumption. right? And if we want to calculate that power to drive that vehicle, that would be equal to force into velocity. Force is half rho A into Ct into B square, which is the drag force into velocity. So, and then the second thing you can see from here that on one hand it depends upon the Ct, which is determined by whether that is a streamlined body or that is a blunt body. And then second thing, it also very critically depends upon the velocity. So it, in fact, it is directly proportional to the cube of velocity. So it means that if you double the velocity, then the power requirement would increase by n times, right? By the local rate. So it is just like that. So now that is the interesting thing, that this is the aerofoil on which I was talking about. This is basically the simulation. You can also do it in ANSYS very easy, because I have also given you some tutorials in which they have done the flow with aerofoil. The upper figure shows the velocity. Now you can see that there is some blue line here, blue area. So that blue area is the area where the flow separation is happening, and we have got a recirculation region here. So it means that here the velocity is almost zero, and pressure is also kind of because there is a flow separation, so pressure is also very low here. So here there is a stagnation point would be in front of it, and then you can see here that as we move away from this aerofoil, the velocity is more. And the bottom graph is for the pressure. You can see a red portion in front of this aerofoil. So this is a flow is coming from here. So here you can see that stagnation pressure is the maximum, or Cp, that is the coefficient of pressure, that is also shows you the pressure. And then here, because there is a flow separation, so there is a negative pressure here, right? So negative pressure is kind of giving us the lift force, which is required for this aerofoil to have some to travel in air, right? So angle of attack, that is the angle between the flow direction and the chord length. So that is 7 degrees, right? So 7 degree, it means that if it is -7, so there would be negative lift when we want to come down this airplane. Then we need to take it down. Then we need to create negative lift. And when we want to take it off, then the angle of attack would be more. But it cannot be more than 14. Otherwise, there is a condition of stall which happens in airplanes. Okay, so now these are the few slides which I have taken from another book, and it would give you the value of CD for different kind of flow situations, like rectangular. This is a square-shaped blunt body, and then CD value for different flow scenarios, and then for here these were for the two-dimensional bodies, and then here we have got some of the three-dimensional bodies as well. So you can also look here are cyclists is cycling and a person is walking. So the calculation of CDs that has been done for these cases. So because why we can calculate this, because this is a non-dimensional property, so we can always calculate it very easily, right? Because it doesn't depend upon the velocity, magnitude, or geometry. So that's why we can define CD values as a function of random number. So I hope that this lecture was kind of introductory for the standard flows. So